Hello dear students, welcome to Axiomatikos. This video is the part of the solution series for IIT-JAM 2020. So we are here with this problem 34 of your paper. This is a section B problem and it is of linear algebra. So let us have a look. Let V be a non-zero vector space over a field F. Let S be subset of V. It's a non-empty set. Consider the following properties of S. So we have 4 properties on S and we have to find out which one is implying which one. Alright. So I will not read these statements. I will read them while doing questions. Alright. So let us begin with this option A. Option A suggests us that first statement will imply third statement. So fourth statement, not the third one. First option suggests us that first option imply fourth one. What is the first option? It says that for any vector space W over F and any map F from S to W extends to a linear map from V to W. Now in this case, please focus on this word any. Any actually means here that whatever map you will choose on S, that map can be extended to a linear map from V to W. Alright. So any map that comes to your mind can always be extended to a linear map from V to W. This is what your first statement suggests us. In the fourth statement, it's given that if first is it is given that span of S is V. So that means if first happens, it will imply fourth happens according to the option A. Alright. So we have to check whether it is happening or not. So I will discard this option by just taking a counter example. I am choosing my vector space to be R cube. I am choosing my S set to be E1, E2. Alright. Now you know that if the space if the vector space is R cube, you know that its basis is E1, E2 and E3. I am talking about the standard basis. Now since E3 is not inside S, therefore you can say that span of S is not equal to V. So this can be a counter example. Alright. If this S, alright, this can be what I am telling you, that this can act as a counter example. Up till now I haven't proved that this S will work over here on the statement 1. That is what we need to prove. Alright. So I am considering my function F as a function from S to W, and I am mapping my E1 to W1, a random element from this, and F2 to W2, a arbitrary or random element. Alright. Now what I want you to notice that this function that I have chosen, this function F, is actually representing every function that can be defined on S. Are you getting my points? It's representing every function on S. Why it is representing every function? Because W1 and W2 are arbitrary. Since it's a function, that means you need image of E1 and E2. So what I have done, I have just arbitrarily chosen W1 as an image of E1 and W2 as an image of E2. So whatever function you choose, you will always get W1 and W2 such that this function which I have chosen is equal to that function that you are thinking of. Are you getting my point? So it represents every function. Now according to your question, according to the statement A, what should happen? It should be extended, this function F should be extended to a linear map from V to W. Alright. Now I am just writing this F bar, a extended map. That is why I am writing a bar on it, because it's an extended map. So instead of writing V, I will write R cube. Alright. Now if you are choosing, let us say you are choosing an element from R cube, then you know that you can write this element as summation AI ei. I is equal to 1 to n. Now see over here that f of v, I am fixing this f of v to summation ai wi. I is equal to 1 to 3. Alright, see this thing. Now it's your job to check that it is a linear map. Are you getting my point or not? This map is a linear map. What is W3? W3 I haven't defined here, but what is W3? W3 is the image of E3. Alright, please keep in mind W3 is the image of E3. So I haven't written it down, but W3 is the image of E3. So it's your job that it's a linear map. Alright, it's very easy to prove that why it's a linear map. Now you have f bar, a extension of this f on R cube. Why? Because if you will place A2 and A1 as 0 and V as even, you will get W1 and W2. Alright, so it's very clear from here that f bar is actually the extension. Why? Because in the f bar also, image of E1 is W1 and image of E2 is W2. Got it? So this one is the extension. Extension actually means that on this set S, this function f bar will act same as that of f. This is the meaning of extension. So we got a linear map. So we have what we have proved up till now, that every map that I will choose on S bar can be extended linearly to R cube. But what you see here, that span of S is not equal to V. Why span of S is not equal to V? Because V has dimension 3 and in your set S you have only 2 elements, so it's not possible at all. If you understand this definition, then you must have got this. If you don't, then you can just look at any book of your linear algebra in order to understand this definition. I cannot introduce it here because this will make this video very long. Now let us move to B option. So from here your A option is incorrect. In the B option, let us check. B option suggests us that first imply third. That means if first this one is happening, then your S will be linearly independent. So what S is actually a subset of V. So it's a set, so we can just write it like this. We are arbitrarily defining your set S. Alright, it consists of element, we don't know whether it is finite, infinite, anything. We are just writing like this. Assume, because in the third option you have to check that whether it is linearly independent or not. What I want you to assume, assume that S is LD. Suppose S is LD, then what will happen, we will check. Alright, suppose S is LD, then according to the definition of LD, what will happen, there exists I will write I, alright, I, such that this Vi element can be written as AJ Vj. J is moving from M to N, where M and N are greater than equal to 1. So this is what I have written is the definition of linearly dependent set. That if S is linearly dependent, then it means that one of the element, at least one of the element, will be written as a linear combination of some other elements of S. We don't know what elements we will have in order to get this linear combination, but we can arbitrarily write that. So we got this. Now in your first imply third actually means that you have to consider first as a true statement. That means if whatever function you will choose over here, alright, you can always extend that to a linear map. This is what your first statement is telling you. Now I am choosing function f from S to W defined by a constant function. Alright, constant function, let us say W naught. So I am defining this function to be a constant function. Every element of S will be mapped to W naught. Got it? So this will imply that image of this element will also be what? Image of this element will also be W naught. This thing is also W naught. But you see from here that because F is a linear map, it means that this thing will be like this, Vj. Are you getting my point? I am using the property of linearity here. Linearity of what? Linearity of F. So F of Vj is what? F of Vj is nothing else. It's W naught, because F is a constant function on S. So it's what? It's W naught. So you are getting that summation Ai of W naught is W naught. Alright. It can happen that we got constant these constant Ai, Aj I will say, not Ai. These constant, it can happen that these constant Aj will be such that the linear combination with W naught will give you W naught. It can happen. I am not denying that. But what is happening here, that this is a first map that I am choosing. We have this information for every set. Now suppose this happen that this thing is equal to W naught, then I will change my W naught to some W1. We don't know what it is. But if I am replacing this with W1, then these combination will again give you W1. So it's not possible, because W1, you can change W1 infinitely many times, because it's a element. All right, it's from the vector space W. You can change it as many as times as you can. So it's not possible that for every W naught belonging to this W, the linear combination with Aj will give you W naught. It's not possible. So this is why we got a contradiction over here. We are getting a contradiction. Now since we are getting a contradiction, that means S, assuming S is linearly dependent, is a false step. So it should be linearly independent. This means this is linearly independent. S will be linearly independent. So according to this, B option must be a true option. Got it? So this is how we can show that first implies second. Now let us move to B and C and D option. All right. So I will be doing this D part initially, because doing D part is little bit good strategy to solve C part. Are you getting my point? So that is why I am doing D part. In the D part, it is saying that second option will imply the fourth one. In the second option, we have for any vector space W over F, any two. So please focus on this word. Any two linear map F and G from V to W satisfying Fs is equal to Gs for all S belongs to S. We have Fv is equal to Gv for all V belongs to V. So your question says that any two linear map will, if they agree on the set S, what is the meaning of agree? Agree means that they are equal on the set S, then they will be equal on the whole vector space. So question is saying, this statement is actually saying that if you choose any two linear map which agrees on the set S, then they will agree on the vector space. If this is happening, then span of S is V. This is what we need to check. All right. So what I will be doing, I will be using the same strategy. Let us consider a set S like this. All right. So it will consist of element like this. Now assume that span of S is not equal to V. Now if span of S is not equal to V, it means that there exists, let us represent it with U. There exists U such that U is linearly independent to Vi for all I. So since spanning set is not equal to V, if you understand the definition of span, you can easily understand this. If you don't, then please look at the definition. Spanning set of S is not equal to V, then it actually means that there will exist a linearly independent element to these element which I have written inside S. Alright. So U is linearly independent to Vi. I have assumed that span of S is not equal to V. Now what I will be doing, from the second statement, if we choose any functions, linear functions such that f and g are linear map from V to W, which satisfies this, that f of S is equal to g of S for all S belongs to W. Alright. So f and g are linear maps from V to W. Now you have that f of, let us map this one. Let us map this Vi. Alright. So f of Vi is equal to g of Vi for all I. Alright. This is what you know, because these are the element inside S. Now what I will be using this. Your question says then we will have Fv is equal to Zv. Alright. But in this case, what I will do, I will map Fu to 0 and G of U to a non-zero element. Then still what I want to explain here, that if I map U to differently than G, then also F and G can be linear maps on V to W. Are you getting my point? So what we have done so far, I will again explain. What is given to us, that we need F and G which will agree on S. So we have taken it. Alright. Now what I am doing, I am mapping U to 0 and G of U to a non-zero number. Alright. You can choose any non-zero number. 0 is the additive identity in W. Now what I am saying, that even after doing this thing, what I have written, F and G will be linear maps on from V to W. Are you getting my point or not? So if F and G are still linear maps and they are not equal to, F is not equal to G on the whole space, then we are getting actually a contradiction. Are you getting my point? So the whole job is now to show that F and G are linear maps. So it's very easy to show them they are linear, because what we know actually, that if F is a linear map, then what you can do, you can assign every basis element to some element of W. Alright. So what we are doing, let us say V is a vector space. So what we will be doing, that inside from S, every element from S, we are mapping it like something like this, that V is equal to G of Vi. Now we are doing that F of U is 0 and G of U is non-zero. It's some other element. Alright. So now let us check the linearity of F. So if you will check the linearity of F, and you choose a random element from this vector space V, then I am choosing two random elements. Alright. So I am choosing V1, no, not V1, I should write something else. So let us say V dash of V1 I am choosing, and I am choosing V2 dash of V1. Now since they are the element of this vector space, so what you can do, you can always write them as a linear combination of the element of S and this U element that we have chosen. So we will get summation AI Vi plus some Bi times of U. So what will happen now? If you will apply this, then what will happen? Alright. F, I missed this F. Now what is happening here is that you can just take this out. Why you can take this out? Because F is linear on f is linear on this s. All right, so you will get this summation ai f of vi, and then you will get bi of f of u. So finally what we are getting that they are linear actually. Are you getting my point? You can now write this as alpha of f of v1 dash plus b of f of v2 dash. It's easy to show. So finally what we are getting that this will be a linear map. All right, so if you define this basis element to some other number than this one, then still they are linear map. So but what is the problem? The problem is that it's not satisfying what we have in this f of in this statement 2, f of v is equal to g of v. All right, so now from here we can say that we are getting a contradiction. That is why our assumption was wrong. Span of s has to be v, because otherwise the f will be not equal to g on the vector space v. So this the option is true. All right, so now in the C option it is saying that second option will imply third one. All right, so now the video is too long, so I will give this as an exercise for you to show that even this happens, you can, even this all the hypothesis that is given in your set S, even this happens. It may happen that S is not a linearly independent set. So for that matter, I will just give a hint to you. Work on R cube and consider your S like this, even, 2 even, or any multiple of it. All right, so E2, and let us say this. Consider this S. It's a linearly independent set, and try to work on this, and even after working on this you will get that this property is always satisfied. You should have E3 here, because all right, you need E3, because right now you proved that span of f is not equal to span of s is equal to v. That is why. So E1 S I am considering to be E1, 2 E1, 2 E2, E2 and E3. So it's a linearly dependent set, and what I am saying that you will be able to prove that it satisfies everything here, but S is not linearly independent. All right, so I will finish this video here. If you have any query regarding this, because it's very difficult for me to explain everything what I have done. It's very difficult for explaining everything that I am using, because this question is little bit tricky and you need deep knowledge of linear algebra to solve this. But I hope that if you understand all of this, then this question will be nothing for you. It's easy question for you if you understood everything what I have done. If you have queries, then you can always ask in the comment section. I will tell you everything there.